because they will need some editing. So I've started recording anyway. So two, it's not just about the waveform that's being used. It is about the signaling, the number of antennas, the bandwidth, and a lot more factors. So if we do a, so next semester you can take up the mobile communications course to get to know that. But this was, this is just a, well, what do you say, the tip of the iceberg in simpler terms. That okay, this is, oh sorry, yeah, this is something that you should know about 4G. 5G, obviously we haven't decided on what to use properly till now. So there is competition between OFDM, 5G, OFDM, most probably 6G. 6G, there is something called OTFS, which is,
So,
yes,
so TSS is the primary candidate.
OTFS is what?
It is primary candidate for 6G.
There is no, OTFS is one of the contenders for 6G. 6G is still 10 years,
Oh,
more than 10 years away. A lot will change in that time. But these days, OTFS is a hot topic for research. So, this. Anyway, so we had, okay, so we lost that diagram. I'll draw that again. So, we had stopped with this diagram that say you have a stream of bits. You have a stream of bits, one. Step two, you do serial to parallel. Serial to parallel conversion. So, you split the stream of bits into multiple parallel symbols. Fine. Map bits to symbols. Fine.
yes, sir.
Fine. Pulse shaping. Then transmission. Fine. Following this transmission, reception, sampling, sorry, FFT, and fine. Okay.
Yes, sir.
Now let the channel have a length L response and on transmitting n things per right? Makes sense?
Yes, sir.
So now for we used Rn, I believe. Slight abuse of notation, but right.
Yes, sir.
So Sn is the symbol sequence. So now at the receiver, what will I do? FFT. So let me take
Yes, sir.
FFT at the receiver. So with FFT, if n I can say right. Fine.
Yes, sir.
Now comes the fun part. We had seen that this was the channel. We had split it into n parts. So if n is large enough, assumed to be almost constant for the kth, right? Agreed?
Yes, sir. Yes, sir.
Great.
Sir,
Yep, Shubhashish.
sir, like for the transmission part, we were mostly be worried about the time domain analysis and rarely went for the frequency domain. But can't we have the similar analysis?
For you, not for the transmission part till now, because before OFDM we have done everything in the time domain,
Yes, sir.
right? So
Yes, sir.
that is some. So that's why OFDM was so radical.
Okay.
Okay, that is why OFDM is something so radical, and that is why we are spending so much time on this separately.
Okay.
Okay. Okay. So this now, if we know Hn, if we know
Sir, am I audible?
yes, but you are on. Tell me, Adit.
Sorry, your voice cracked in between. You were saying that. Am I audible?
Yeah, you are audible. There's a lot of noise, but you are audible. Okay. Now you are not audible. Okay. Anyway, if we know Hn, then agreed.
Sir, H of what you have written capital H of?
Sorry.
Sir, you have written capital H of K or capital H of L?
Capital K. Hk is the Fourier transform of Hn.
Okay. So it is K. Okay.
Okay. Endpoint Dft or endpoint Fft. Fine. Also, W1, W2.
Sir, am I audible now?
Yes, you are audible now.
So, sir, I was asking that you told that the difference between OFDM and FDM is that in OFDM we use orthogonal frequencies, but sir, in FDM also we use these. Divide the whole frequency domain into equally spaced frequency levels, right? Where we send different symbols across them.
One, not equally spaced. Two, we
Okay.
would require guard bands over there.
Okay, so in OFDM we have these the carrier frequencies themselves are orthogonal. That helps us to not have the guard bands.
Yes.
Okay, sir.
Okay. Unknown samples of noise. Fine.
Yes, sir.
So and these form a sequence. So this I can write this vector W. This let me okay, capital W. The vector W as doesn't matter since we have used 0 to n minus 1. I will stick to that. Fine.
Yes, sir.
Since I am taking the FF and W.
Sir,
Yeah.
sir, previous you took n from 0 to capital N, like both included.
No, in OFDM I took 0 to n minus 1 endpoints.
Sir, here you took. Okay. That's okay.
Less
Okay.
than. That is less
Yeah.
than. Less than. Fine.
Yes, sir.
And now letting F be the DFT matrix. You have in your DSP course, have you looked at the matrix interpretation of DFT?
Yes, sir.
Yeah, so you know what, there is something called the DFT matrix.
Yes, sir.
Okay, great. So therefore, this vector W equals right,
Yes, sir.
or FW, not exclamation W, FW, fine. So covariance of W is fine. What does this mean?
Sir, why are we taking n naught by 2? Like, is it a real?
No, okay, wait just a second. Let me think. Yeah, it should be n. It should be n naught. It should be n naught. Fine. Okay, sorry. I wrote something right in the first attempt, then made it wrong. Yeah. Fine.
Yes, sir.
So this. Now, therefore, the entries of W are also IID Gaussian with variance n naught and sounds right?
Yes, sir.
Yes, sir.
Yeah. Okay. Therefore, Yn equals, or Y rather RK.
Sir, W is complex Gaussian, no?
Yes.
So you read the entries of.
Fine.
Okay. Yes, sir.
Fine.
Yes, sir.
Yes, sir.
So, if the kth OFDM stream draws symbols from a constellation, if the kth OFDM stream draws symbol from a constellation Sk, then I can calculate the bit error rate. Fine.
Yes, sir.
We can use symbol error rate for the kth stream and hence for the time. Fine. The next thing is,
Sir, sir, in this case, while calculating the bit error or symbol error rate,
yeah.
so we have to take into the account the channel as well, no?
Yes.
So what means, how do we have to treat the channel, Rayleigh or Gaussian?
Channel, that is the thing that I said. Channel is answers your question.
Okay, sir.
Channel is known. So what you will do is, just a second. So since we shall ask this question, let us, for example, consider BPSK with special cursives. Fine.
Yes, sir.
Yes, sir.
So or rather minus yes, yes. Fine. Just so what we will get is fine.
Yes, sir.
These are the two possible symbols. Then draw this. The bit error rate is symbol error rate is PE comma K equals Q of right.
Yes, sir.
Sir, and not by 2.
Yeah, 2 numerator. Fine. Fine. Sorry. Yeah. Fine.
Yes, sir.
I'll write it again just for clarity. Fine. So you
Yes,
don't
sir.
have to worry about Rayleigh, Gaussian, all those things. We will talk about that once we reach fading channels. That is next week. So next Wednesday and Thursday, you don't have you have holidays, right?
Yes, sir.
Yeah. So I'll be taking classes. I'll just finish off the course during that week because tomorrow and day after are off, or I won't be taking classes tomorrow and day after. So next week I'll possibly take another couple of lectures and finish things off. Fine?
Okay,
Sir,
sir.
Yeah, great.
so like after the next week's lectures, like we'll have a quiz or direct viva.
So what I'm planning is I'll take vivas and that will give you enough time to prepare for the quiz. And then post the vivas, once everyone is done with the vivas, then I'll float around the quiz for 1 hour. Fine?
Okay, sir.
Sir, instead of the quiz, can we have a long assignment as was in the course plan?
Okay. Okay. But so your quizzes have reduced to long assignments now. Timed long
Okay, sir.
assignments. That is. See, the course plan was, I made the course plan thinking that I will be able to make multiple choice questions. But it turns out that the content is, or content of this course is not that amenable to multiple choice questions.
Yes,
Even
sir.
if I, even if I try to make multiple choice questions, actually, if I try to make multiple choice questions, you guys will be at loss because then I won't be able to do step marking.
Yes, sir.
Yes, sir.
And one wrong step and boom, everything is lost. So that's why I'm not in favor of multiple choice like questions this time. This now this will be slightly confusing. So let, because we used capital R for the received symbol, but we also want to denote the achievable rate.
Sir, one doubt.
Ah,
Sir, is it enforced that h of k will always be positive?
good question. See,
Yes, here it doesn't matter, but sir, when you drew the diagram with the symbols,
yeah.
you
So
have
actually, this is you are right. Actually, if I draw the diagram, HK can be anything. So you have to have the axis aligned with that HK. So you can always align the axis of decision with HK and reduce it to this.
okay.
Okay. You can always align that axis. So I took so this is the aligned axis, you can say. So now let's abuse notation for a while. Let Rk denote the achievable rate over the kth. Fine.
Yes, sir.
Okay, let me do it this way. Let's see K. Denote the capacity of the kth channel. Fine. That will avoid confusion. Ck equals half log to the base 2 1 plus or the kth data stream. Fine.
Sir,
Yep.
shouldn't there be the B outside the log? Like, ordinary. Okay.
Okay. So the total capacity is k equals 0 to n minus 1 log to the base 2 1 plus right?
Yes, sir.
And in general,
Sir, I think we are missing a half.
huh?
We are missing a half.
Average.
1 minute. Okay.
You're right. Want to maximize in general, we want to maximize this average capacity subject the total amount of power that we spent fine.
Yes, sir.
So I can write therefore write this as an optimization problem. Write this as an optimization problem where max c equals 0 to n minus 1 1 plus subject to P total Fine.
Yes, sir.
So what do we do now? So now let me ask the question properly. Now, choose P1, P2, Pk minus 1. Add up to Pkt and maximize the average spectral efficiency. Another name for that testing. Fine.
Yes, sir.
So what do we have now? Or how do we solve these kind of problems?
Lagrangian.
Yeah, Lagrange multipliers, not Lagrangian. We'll define J equals C plus lambda summation k equal to 0 to minus 1 pk or just to make life simple later C plus lambda p minus, because this will lead to a negative minus sign otherwise, because this won't change anything, just that this will be slightly more convenient in terms of notation. Fine.
Yes, sir.
For this or for now,
Sir, P here is
yeah, total power, P total. Fine. No.
sir. Wouldn't P total isn't P total is equal to the sum of k is equal to 0 n minus 1 pk.
Yeah.
Oh, okay. We are maximizing. Okay.
Yeah. This is how we solve optimization. This is the constraint. This is how we solve constraint optimization problems.
Yes, sir.
Yes, sir.
So now for optimizing this del J by del Pk equal to 0. Fine.
Yes, sir.
1 upon let me. So for the kth term, the only non-zero terms will be 1 by 2n log to the base 2 1 plus k pk divided by is lambda p total minus pk. Right? These will be the only terms dependent on pk. I'm just separating those out from the summations.
Okay, sir.
So you can have a summation, but so differentiating this 1 upon del by del pk, del j by, let me call this. So del j by del pk equals 1 by 2n. So log of 1 plus so just checking, the derivative of log of 1 plus x is same as the derivative of log of x, right?
Yes, sir.
Yeah. So square pk.
Sir, but in the denominator, we'll be getting 1 plus x.
Yes, sir.
You will be getting 1 plus x. Yeah. That was what I was.
Like not 1
Yeah.
1. Yeah, exactly.
This times because of the chain rule. Fine.
Yes, sir.
Minus lambda. Fine.
So dj by d p total by dpk will also be 1, right?
P total is a constant.
Oh, okay. Okay.
Fixed constant. 0. The derivative will be 0. Fine. So 1 upon 2n k square pk by times square or so I will move all the constants on the left hand side, on the right hand side, and take the reciprocal. Fine. 1 plus
Yes, sir.
k square pk will not be equals and not hk square let's not move this there. So this. Fine. So let's keep the dependence on k on the left hand side. So this is and not b Okay, let me do this step by step. That will be easier rather than trying to mess things up. So I take the reciprocal 2n times 1 plus hk square pk equals k divided by hk square by b. Step 1 fine, guys?
Yes, sir.
Yes, sir.
Yeah, so step 2, I'll move 2n to the right hand side, and yes, I'll move 2n to the right hand side. So and divide. So what's wrong with this thing?
Sir, what is our aim exactly? Like, what are you trying to equate?
Find these P1, P2, Pn. Find the power. Find the powers that maximize the capacity, average capacity.
So then we can simply divide the HK square by N naught by B that we are having in the denominator.
So one, I'll do two things. One, we'll solve this, and you agree that this is mathematically optimal what we are doing,
Yes, sir.
and so we'll solve this and see if your solution matches with the optimal solution.
Okay. Okay, got it.
So you can check and see if your solution and the optimal solution are the same. So N naught B divided by HK square plus PK equals 1 by fine.
Yes, sir.
And oh, I missed one thing. So this is log, right? Log to the base 2. What's this? This should be there. I hope you remember.
Yes, sir.
Fine. Okay. 0.693. Did you guys have to memorize this in your JEE days?
Sir, we didn't
Yes,
work
sir.
with.
Sorry?
We didn't work with log 2.
No, log e to the base 2.
Yes, sir.
This was required in
Okay.
physics,
Yes, sir.
in half-life and all those calculations.
Yes, sir.
So last week while cleaning, I found my class 12 notes as well. I had memorized the entire periodic table somehow, magically. And now I cannot remember even one row. Sun eta. Fine.
Yes, sir.
Or summation k equals 0 to or pk is, but pk is eta minus right. Therefore,
Yes, sir.
now I can back substitute this. N eta minus sorry. Fine. So this is how we find eta, and one interesting thing is that if the channel is too bad, then HK will be small, right? Agreed?
Yes, sir.
Therefore, N naught be over this term, this will be large.
Yes, sir.
And PK will be negative. Agreed?
Yes, sir.
So if we end up with a negative PK, okay, so battery is about to die. If we end up with the negative PK, ignore that channel, reallocate power into all the channels with positive power and fine. You get what we are trying to do here? Yeah.
Sir, but we are already having optimized power for all the other channels. So this reallocation won't be.
No, it won't, the reallocation won't be suboptimal because then you are not considering that subchannel into account.
So reallocation is indeed suboptimal.
No, so no. You can try this out. You can try this out. You have to write the MATLAB code yourself. Reallocation won't be suboptimal because you cannot transmit on a negative power one. If the so the point here is that if the channel is so bad that you have to, or if the channel is too bad, then you don't transmit over that channel. You assume that the channel doesn't exist. You only transmit positive powers. You can try this out yourself. And this algorithm is called the water filling, or this is called the water filling approach. So what happens is that if you have to level a surface by filling water into over a lot of poles. Suppose there are a lot of poles, and you have to level the surface by putting water. So you don't put any water onto poles that are already above the average water level. Okay, so we are out of time, and the laptop is almost out of battery. So I won't. Okay, still 20%. So this is called the water filling approach. You can try this out yourself. So at first, even I was, so when I read this first some 11 years ago, even I was confused that how can this be optimal? But experimentally, you can verify that this is optimal, or this is the optimal solution.
So alternatively, can we say that means if the channel is too bad, then the probability.
If a specific sub channel is too bad.
Yeah, then the probability of error in that channel becomes.
We are not talking about probability of errors. We are talking about the channel capacity.
Okay.
Okay. So the idea is if the channel is too bad, don't transmit. Consider that as a blank subcarrier. Channel is too bad. Simply consider it as a blank subcarrier. Fine. Okay. So I believe it's a good time to stop here. We'll continue next Tuesday or Saturday.
Okay, sir.
I'll text you guys on Saturday. If people agree, then we'll continue on Saturday. Otherwise, we'll continue next Tuesday. Fine?
Thanks, sir.
Okay. Bye. Have a nice day, all of you.
Bye, sir.